Why it is not coming? Don't know. Turn off your camera again and camera. I'll log out again. I'll start or what? It is not. It is not the video mode. Okay. Let us log out. So it is visible now. Hello? No. It is showing now. Maybe there is a problem in camera. Audio is good. Audio is
Your picture is not visible.
maybe some camera problem, I don't know. Okay.
Okay, sir.
But then how, let us see whether I'll present it or I'll go to my department. It will take some time. I'll go to my department. Let us see. First, I have to check. It is happening. So the slide is, you are seeing it, slide? It is visible, side?
No, sir.
No?
No, sir. No, sir.
How it is happening? Not visible?
Yes, sir. Visible. Yes, sir. Visible.
Okay. So then forget my face. Okay. Because if it is audible, it is fine. Because otherwise, if I go to department, 15 to 20 minutes, I will be stopped then. Okay. So fine. So as already I mentioned, like physically I have gone to the department. So now, like, so what is the background? So most of your students, no? BSc students many, how many, and teachers. Okay? Yeah? So, mostly the audience are more students, no, many students are there in this group. So it is audible now? Yeah? It is audible?
Yes, sir.
Okay. Okay, so now I'll talk about the basic concept of optimization and where we can use it. So basically, that has already Mr. Babu mentioned, that this is title of the talk already mentioned and what is how related optimality with respect to optimization. So basically, the notion of optimization we use knowingly or unknowingly everywhere. The starting in your daily life or where you are going marketing or everywhere taking a break or studying online classes, webinar, whatever. So we are using optimization. So starting with timing. Suppose the seminar started at 7 o'clock or 6 o'clock, then whatever audience get, okay, and again, 11 o'clock. But the thing is, even in morning, you may not get, you will get audience, but that time your network is very good. That is correct. Working. So last time what we did, today compared to online test, accelerated. Because before it is very slow and then a day on the test in that. So that means we are optimizing the time, like where you get the your goal is to complete the exam rather than time. Suppose you say, no, why not between 11 o'clock? Because we have the constraints. We have the restrictions at 11 o'clock. It's not like network traffic is fine because all over all places of India, which are local time, they use the network. So of course, we will face the difficulty. To avoid this, sometimes we change the time. Okay, because but anyhow, that was the exam. Not a formal discussion. But in that exam means what? Everybody will at the end, last 5 minutes, everybody will submit their assignment or their exam papers. So in that, the networking, how you optimize because that 5 minutes. Okay, for which because again you have to optimize your networking in such manner that the company will not lose its place. Like very example we have had this everybody like your disadvantages is that unless you pay, you cannot teach for more than 200 or 300 like this. And recording facility is also not there. Okay, and but if you pay and you have a register version, then something can be done. But it is very user friendly to implement. But one of the alumni of IIT requested us that basically I am going to the math one of 2000 student, first year student, he joined this engineering this year. So he requested me to see how I am relating to optimizing problem. He requested me to, because as I am alumni of this institute, I am keeping the network field, so no problem, because that time he can show this his load that this many students I have handled, including IIT Kharagpur. So he will do more business rather than giving some small things to IIT Kharagpur, but he learn it in lab. So that way we are managing. But what happened? We are managing the lectures, etc. But here again we start doing more, asking more people to join in different subjects. Then what happened? Happened after 15, 20 days, his server becomes disturbed. One to the student. So that means what? The network issue. During that time, all the classes we are assessing. See, I am taking 11 to 12. That doesn't mean only I am teaching. There are another 5, 6 teachers subject also they are teaching independently. So that means that load, etc. So this part he has not pointed out and he has not considered into account. So then the server uh, becomes slow and finally we didn't access. So finally the next day I said thank you and I quit this prep buddies. But if you could have modeled this optimization problem say, into his server that way, okay, how many students, how many different lectures at a time I can arrange in my webinar, in my like video mode online thing. So if you could have done that, so certainly this problem would not have taken place. So finally we left everybody now is requesting etc. Because once we are doing business, you see if we are losing 1 hour, one day lecture means so how will adjust those lectures? So that way, like even if in the whatever morning also started also again same thing happens. So once you model it and you take all those data, all the constants, what are the constants like here, the constant is 11 o'clock, traffic is heavy here, so many classes, etc. Because everybody is doing that. So that way it would have taken care. So that is the reason. Now for conducting exam now, arbitrary timing we are not giving to the student. We have limited slot now we have. And that time no other test also. Otherwise, an exam also you cannot conduct. So it is just knowing this scenario, we are changing our plan. But before going to do it, if you could have modeled it mathematically and you just taken all those data and say, okay, fine, it will load up to this many bit any hour. But maybe in the traffic hours or whatever, because that time you can restrict number of participants or number of lectures everywhere, including your vaccination also. How how smoothly you can do to everybody. Again, you have to take these models and that way you can just start. So in this way. Okay, so everywhere we just use optimization, but as like how to do that. So in optimization problem, we just come with either maximize or minimize. What is that? We call it optimize or extremize. So it is either of a maximization problem or a minimization problem. You have to maximize your profit and you have to minimize the loss. You understand? So this is the two concepts. Most of the time, maximize, you are maximizing. You have to maximize your grades, your marks in your university exam. Okay? And you have to minimize the number of question you are living during the exam. So everywhere, so sometimes what as a student you do, okay, I will just read first to last, which questions are easy, I can do fast, etc. Because in the end, maybe I may not get the time, etc. So that way, there also you are using the optimization or technique, etc. Because time bound is fixed. Okay, so that way you have to do yourself, like manipulate and just here rearrangement the things, questions that I can do that. Because if that at the end, suppose time is over, you have not solved a easy question. Then after that, just why I have not don't I have gone to that last phase, why phase? Okay, so that is what. But you have another problem. But if you could have attended this problem during that time bound, you could have scored. Okay, so this is what optimization problems most of time in your daily life, like we use and this optimization started when calculus started, like those ages also in form of mathematics. We just model because unless mathematics means what we have a model and how we solve that and get a solution. So whatever mathematics we are studying in that way, we just proceed. Okay. So now come to the basically I will just talk about because some from this I will also only fundamental basic concept I will just teach and those who will work in some field like in some of the faculties you can also concentrate more on those news areas that also I speak. And also, you can, if someone is interested to higher research also. So those areas, this Harrison inequality, complementarity problems, and equilibrium problems also, you can concentrate. So knowing those, that is what is the latest problems we have solved, etc. And it is basically applied in uh, any branches of mathematics, including engineering and management also. Okay, so in that case, like in so already I have already mentioned this. So given we have a function from is set is a subset of the R to R. We have a function. So what is our? We have to find an element x0 from the set A such that f of x0 less than fx for all x into. So this is what is called minimization. So because x0 is a point for which f of x0 gives your smaller value in this domain A. Okay, and if we will say that f of x is greater than fx for all x in A, then it is a maximization. X0 is a maximal point, or f of x0 is the maximum value over that set A. Okay, so basically you have to write either maximize the function fx over the domain or minimize the function over the domain. So such a problem is called an optimization problem or a mathematical programming problem. So this term is not directly related to computer program. Okay, so like someone said that it may be related to computer programming. Okay, so but we use the term programming. So basically the term is the old one, the like we use that time to get funding because you are using your work in some real value, in some real life applications. So to get fund or generated fund, the terminology programming we added, and still this it is not related to computer programming. So the term basically that how well you are using this thing, okay, and to get more fund, this like linear programming problem. This is also one type of programming application. Okay, so now many real world and the theoretical problems may be modeled in this general framework. Problems formulated using this technique in the field of physics and computer vision may refer to the technique as energy minimization. Speaking of the value of the function f as representing the energy of the system being modeled. So that is what this function as a mathematics point of view, we say it is objective function, but for physics, it becomes that they are energy minimization problem they are talking now. Okay, but whatever they are telling, but the thing is their goal is to find a solution. That's what we are doing, and they are using in their problem. Okay, so they are telling that energy minimization problem because they are minimizing. So in that case, we use it in any place. Okay, So typically, take the subject of the Julian space array. You just tell everybody to mute like when I am speaking, and if question section using question type, you will unmute and speak. Otherwise, it's difficult. Okay, so the elements of A are called feasible solution. The function F is called objective function. So basically, the terminology we can use by objective function means what? What you are minimizing or maximizing effect subject to that point. So that subject part is called constant part, and the minimize or maximize is called the objective function. And the domain where we are considered these points, that is called feasible region. Okay, and you just from that feasible point, you just randomly search, and finally you will claim that using the figure to that this point is a minimum point or a maximum. So as we have minimized, we are minimizing or maximizing the function subject to some restriction. Okay, so any optimization problem can be written in this minimize effects or maximize effects subject to x belongs to A, where A is the feasible region of this. Okay, so in that case, we have the domain also of A is called the subspace, subspace, while the elements are called the feasible solution. Elements are called feasible solutions, but the entire that is called subspace to get the solution basically, or you can say feasible domain also. It's called a feasible domain, and the points are called feasible points. Okay. So generally, when the feasible region or objective functions of the problem doesn't present convexity, there may be several local minimum or maximum where local minimum are defined at the point for which there exists some delta such that in this domain, x star is a minimum value. But there I have, if I consider f of x star is less than f x for all x, then it's a global minimizer. Okay. So local maximum also defined, just interchange the sign of this here, that less than becomes greater than. Okay. A large number of algorithms proposed for solving non-convex problems, including majority of commercial available solvers, are not capable of making a distinction between local optimal solution and rigorous optimal solution, and we treat the former as actual solution to the original. So basically, for linear programming, getting the like solution, this solution, you have to take the help of the approximate solution, because now our computing ICT is so good that from the local solution also you can get a global solution for the given optimization. So the branch of applied mathematics and numerical analysis that is concerned with the development of deterministic algorithms that are capable of to actual optimal solution of non-convex programming. So basically, even if this global solution, I am not finding out, but we start with the local solution, then using if you know the existing solution, and using convergence analysis, you start with a point from the algorithm, write a algorithm for this, because you are doing non-linear optimization. So in that case, you have to do some good algorithm to get the non-convex. But for convex programming, you can get it the solution, but again the complexity. You will find the gradient also the time complexity. Okay. So the nutrition we do here optimizing problem are often expressed in this form. What I mentioned, minimize x square plus 1 x below 1. This is what is called a on-constraint optimization. So there is no restriction of the domain. This R is the entire right of this. So this acts for the minimum value of the opposite function x square plus 1, where x ranges over the real number r. The minimum value of this case is plus 1 because when x is 0, the minimum occurs. And when x is for this r only, when x is not 0, because it is going on, in that case, you will see like it will. So the minimum occurs at origin only here. So because it's a positive function, because minimum of x square plus 1 is same as minimum of x square plus 1. So minimum of a quadratic function, positive function occurs at x equal to. So that 0 is a global solution. To come to this, maximize 2x, x belongs to 1. Okay, so this is a maximization problem. This asks for the maximum value of the objective function 2x, where x ranges over the reals. In this case, there is no maximum. If we draw the graph, okay, passing through origin, y equal to 2x, you could say. So there is no such maximum as the objective function is unbounded. So this line passing through origin, it is unbounded. So we cannot find the maximum value of this. But it will restrict it over some bounded domain, because that's what that maximum minimum occurs for a real value bounded domain on equivalent space. Okay. So here, as I mentioned here, there is no maximum. So here, the answer is infinite. Now come to this. Argument minimum in the negative x-axis ends at -1 x square plus 1. So this asks for the values of x in the interval -infinity to -1. So the negative axis ends with -1 point. So that minimizes or minimize the objective function x square plus 1. The actual minimum value of that function doesn't matter. So in that case, the answer is x equal to -1. So here, you go for -2 here, again you will get bigger value. So here, the minimum value of the function occur at x equal to -1. So if it is x equal to -1, putting x equal to -1, we are getting 2. Okay. So now come to another problem. Argument maximum. Okay, so the word argument we basically use here. So that means not necessarily over this domain, because you are not optimizing the entire real life. Like argument minimum of this objective function plus 1 over this interval -infinity to so here is what's called argument minimum. So this is most of classical book are this notation. So here never say that plus 1 x belongs to 1. Its minimum occurs at origin. But here now we have -1 workers because we have changed the domain. Now again, this domain is unbounded domain. But even if unbounded domain also, we have a meaning. Okay. So now come to another problem. Cos x, cos y, x cos y. Argument minimum x belongs to -5 to 5. So this ask for a pair XY that maximize or minimize the value of the first Y. Okay, with the added constant that X lies in this interval. Because the argument maximum minus 5 to pi. Again, the actual maximum value of the expression doesn't matter. So over minus 5 to 5, we are looking. Okay. So this terminology we are using argument maximum here. Okay. So easily can find the solution pair because we are are the pairs of the form 5 to pk and minus 5 to k plus 1 p, where k ranges over all integers. So we have so many local minimum or this objective function. Okay. So now come to this. So this field like majority of field available in mathematics. Linear program. The pairs of the linear programming studied the case in which the objective function f is linear and the set a is specified using only linear equalities and inequalities. Such a set is called a polyhedron or a polyclone if it is bounded. So in general, polyhedron is not bounded, but polyclone is bounded. You just take intersection of all equalities. So then, this is what is called the bounded domain that is also called polyclone. Okay. Then, so this is what is called linear programming. That means the objective function as well as the constant set. That equations all are linear. Then we call it linear. What is integer programming problem? Integer programming studies linear program with some or all variables are constraints to take an integer. So the integer programming here, you cannot take 1.5 or root 2 or minus 2, 3, etc. You cannot. Because with respect to positive integer we are considering. It will give negative integer also fine. Then you have to write that. So integer programming studies linear program in which some or all variables are comes to take integer value. So as it is integer value, so we can take both positive negative also. So there is no harm. This is what is called integer program. Then what is called quadratic program? So the quadratic programming allows the objective function to have quadratic terms like x square plus 2x plus 3. So we have a quadratic equation here. Two-dimensional case. In case of n-dimensional, we have x to the power n, and we have this values also. So it is with like quadratic, basically the terms like quadratic as it is there x square type, but in matrix form I have to write x transpose qx, where q is a symmetric matrix, x transpose qx. What's the general matrix also you can take plus some bx plus so that way quadratic programming is then your nonlinear programming. That's when the problem is not linear, we call it is a nonlinear program. Okay. So nonlinear programming studies the general case in which the objective function or the constraint or both constraint. So that way nonlinear. Okay. So maybe nonlinear means which is non-linear. Suppose the objective function is linear, but the constants are not linear. But many are linear, but one is non-linear. Then also it is non-linear. For linear, you have everything linear, including this, including your objective function also. And if they are like we got minimize x square plus x. So that square quadratic, the square term is there, so we cannot say it's a linear programming. Whatever may be there in that, maybe the constant part or all are linear inequality. But here, as it is not a linear programming problem, then you have to go with objective functions where both nonlinear parts also there. But how to handle this? So in general, solving nonlinear programming is not easy. So to because everywhere, including your differential equation also, what you are studying. So you cannot solve a differential equation also in general. But we can solve a nonlinear differential equation if it satisfies some of our existing properties. Okay. So when nonlinear programming is coming here, so we have to take the help of the approximate solution for the programming problem. So there you have to start with the initial guessing solution and how smoothly you can approaching to the original solution of the given optimization problem. So that is in case of nonlinear programming, you have to write an algorithm. You have to implement an algorithm where the global solution is optimal condition of the local solution. Like where it is. Okay. So then what is called convex programming. So it just studies the case when the objective function is convex and the constraint is any form a convex. This can be viewed as a particular case of nonlinear programming or a generalization of linear or convex quadratic programming. So you can say as a generalization of linear or convex quadratic programming as a convex. So it contains everything. Okay, so linear programming problem contains convex quadratic programming and your this also your quadratic programming also because that restriction I met and where the adjective function becomes convex. Okay, and so here it is if both objective function and constraints that the region generated by the constraints is a convex set, then we will call it a convex programming. Then come to semi-definite programming. So as this title said, something about semi-definite programming. So it's a subfield of convex optimization where underlying variables are semi-definite variables. So there you are taking the variable as x, but I can take variables as some small x. Okay, so in that respect, so we have what is called semi-definite programming. It is generalization of linear and convex quadratic programming. Then what is stochastic programming? Stochastic programming studies the case in which some of the constraints or parameters depend on random variables. Okay, so that part I am not talking about, but stochastic programming is also there. So we have this random variable, that parameter, the constraints or parameters depend on the random variable, and combinatorial optimization is concerned with the problem where set of feasible solutions is direct, discrete, or to be reduced to a discrete one. So whether the solution is discrete, right? Then from those set of points you can try with and update your solution. That is what is called combinatorial optimization. Okay, and infinite dimensional optimization problem. So infinite dimensional optimization studies case when the set of feasible solution is a subset of infinite dimensional such as space of functions. So infinite dimensional optimization. So we have see there we talked about subset of Rn, but now I am talking about subset of infinite dimensional, subset of functions. There we don't have the notion of finite dimensional. Then constant satisfaction studies the case in which the objective function f is constant. Thus, is used in artificial intelligence, in particular in automotive. Okay, so this is there. So now, government, like here, most of um, um, government department, this constant satisfaction problem they use, and like artificial intelligence and automation also, like we have now machine learning, artificial intelligence, those area where constant satisfaction problem is used. Disjunctive programming also used to where at least one constant must be satisfied but not all of particular using scheduling problem. Okay, then trajectory optimization is the specialty of optimizing trajectories for air and space vehicles. Like that, what? Those are trajectory optimization problem. They, you are that new this rover is landed there in your Mars. So they are using the help of trajectory optimization program. They are monitoring here in the every angle, every second, what the that what they are doing. That in this Mars rover, they are just monitoring here. Okay, so what our so this is what through trajectory optimization problem because the dimension here infinitely many times. That is infinite dimension. So finite linear programming problem will not work. Okay. So in a number of subfields, the techniques are designed primarily for optimization in dynamic context. That is decision making over time. So calculus of variation seeks to optimize an objective defined over many points in time by considering how the objective function changes if there is a small change in choice of path. So these are the terminology we use in calculus of variation. So like objective, suppose there is a small change in optimality in your optimal solution. What is the corresponding changes in the objective function? So then we have the optimal control theory is a generalization of calculus of variation. So those are also infinite dimensional problem. Dynamic programming studies the case in which the optimization strategy is based on splitting the problem into smaller subgroups. The equation that relates these subgroups is called Bellman equation. So here you can look for the Bellman, what Bellman did. She just break the problem into some smaller problem and just start with solving the smaller problem and combining all those solutions, you get the solution of the smaller subgroup. So now the technique. So for twice the functions, unconstant problem can be solved by finding the points where the gradient of the objective function is. That is the stationary point. If partial derivatives exist, using the Hessian matrix to classify the type of each point. If the Hessian is positive definite, the point is a local minimum. If negative definite, a local maximum, and if indefinite, it is some kind of shadow. However, existence of derivative is not always assumed, and many methods were derived for specific situations. The basic classes of methods based on smoothness of the object functions are combinatorial methods, derivative methods, first order methods, second order methods, actual methods falling somewhere among the category above in. Okay, so that is above that what I discussed. Then we have the gradient descent also, known as steepest descent or steepest steepest acid, Nelder-Main method, also known as AMOVA method, subgradient method, similar to gradient method, in case there is no gradient. Simplex method, ellipsoid methods, Newton's method, quasi-Newton's methods, Newton interior points method, conjugate gradient methods. So this terminology you can check it and see how they are defined. So at least those are interested in some work in this area, and you can take like what the conjugate gradient. So can you add something in that conjugate gradient method? So people are working in that area and they are doing the line search, a technique for one-dimensional optimization, which used as a subroutine for other more general techniques. So basically, here line search a technique for one-dimensional optimization. Just move from one point to next, for which you have to update it. That means for second problem, second point, so it will minimize. You will get smaller than compared to the first point. So then you just go on searching in this way. That is what is called line search method. Or single value problem. So should the objective function be convex or there is of interest, then any local minimum. So easily we can prove if the function objective function is a convex function and we have a local minimum, then it must be a global minimum. So that means for convexity function, we have a function which is convex, then it is enough to find its local solution which gives you the global solution because the function is a convex function. Okay, so now constraint problem can often transfer one constraint problem with help of Lagrange's multipliers. So some work also we have done regarding this, how to convert a constraint optimization problem to unconstrained and solve the constraint with respect to unconstrained. So this concept also we have done it, and also we are working on how we have different objective functions. We have because every problems now we are converting to a new problem, unconstrained one. But how to solve this problem again with respect to this previous algorithm, we can do it. So this concept. Okay, so here are a few other popular methods. Hill climbing is an optimization technique which belongs to family of local search. Simulated annealing is a genetic problem, probabilistic meta algorithm of the global optimization problem, namely locating a good approximation to the global optimum of a given function in large space. Okay, so this is also another like you see that in some of the engineering application they are using this SM methods. Quantum annealing, this also we have beam search, genetic algorithm, stochastic tunneling. Is also an approach to global optimization based on the multiple method, sampling or the function to minimize. So problems in rigid body dynamics, in particular rigid body dynamics, often require mathematical programming technique. You can view rigid body dynamics as attempt to solve the ordinary differential equation on constraint method. Constraint are various non-geometrical geometry constraints such as these 2 points must also coincide. This surface must not penetrate any other, or this point must always lie somewhere on this point. Also, the problem of computing contact forces can be done by solving the linear complementative problem, which can be viewed as a quadratic programming problem. Many design problem can also be expressed as optimization problems. This application is called design optimization. Okay, so one recent and growing subject of this field is multidisciplinary design optimization, which will useful in many problems, has in particular been applied to aerospace engineering, program economics, and relies heavily on mathematical programs. An often studied problem in microeconomics, the utility maximum function, and its dual problem, the expenditure minimization problem, are economic optimization problem. Okay, so this is also used in interdisciplinary, multidisciplinary design optimization. Okay, so in general, consumers and firms are assumed to maximize their utility. Firms want profit and they use more that way. So also, agents are most frequently assumed. Okay. So in that case, your this asset price are also explained using optimizing through underlining the theory is more complicated than simple utility or profit optimization. Trade theory also uses optimization to explain trade patterns between nations. Another field that uses optimization technique extensively is operation research. That what the sub branch that is operation research, which deal with linear programming little bit and integer programming, linear programming, whole linear programming, and integer programming, and some network programming that also again related to linear programming, and basic theory of nonlinear programming. That's more some KKT condition. Okay, so now the history. The first optimization technique, which is known as the descent step, goes back to Gauss. So when, as I mentioned, so I am not doing this again. That when calculus started, the optimization problem started. Okay, so these are the persons. So John von Neumann, Leonid Kantorovich, Boris, this modern mathematician, Oleg, Michael J. Todd, Richard Bellman, and this is okay. So this part, the technical part, you can go through it like traditional inequality. Very recently, in the 1966, studying seeing some problem, then they solve traditional inequality problem through optimization. Okay, so this theory is also so. Sri Babu, is it time? I can continue or because it's just 1 hour, I think. Yes. Sri Babu, hello. Can I continue? Sri Babu, is it time? I can continue or disconnect? Some echo is coming going on. Yeah. Can I continue? So this so basically variational inequality problem is a problem of this type. So this is the inner product. We have a function from k to Rn. So this is. So here we are not minimizing. Find a x such that this is greater than equal to 0. Okay, but how can convert this problem to a optimization problem? So that we have to rewrite in terms of optimization problem. Then this variational inequality problem can be solved through optimization. Here we are not. So in general, so this is also in this analysis sense also we can do it, but this part I am not talking because it is difficult for you. So now this this problem also you can visualize as a variational problem. Minimize effects over this interval AB. Also, this example I have given, you can say this. Okay. Then what is the equilibrium problem? That's what people are using. And this mathematics field, we don't have Nobel Prize, but the person who that equilibrium problem, NASA equilibrium. So this mathematics model, but in name of economics, game theory, he got the Nobel Prize, not in name of mathematics. But this mathematics he are derived. So what is bi-equilibrium problem? Bi-equilibrium problem means we just find a function from subset of Rn to R of this type. Okay, so that is f of find x bar for which f of x bar y is greater than equal to 0, where f is from k to kr and it is 0 on this diagonal. Okay, and easily can show that f of xy and f of ys, that's all, is also negative. So this problem contains as a special case for initial optimization problem of NASA equilibrium. Okay, so now just I'll take this problem, how I'll write optimization problem with respect to, okay, and easily can your additional inequality or equilibrium. So just take minimize phi x belongs to k. You just define f of xy as it's defined by phi y minus phi x, because the function is given supplied to you. Then f of x equal to 0 and f of xy equal plus f of y is equal less than equal to 0. This is less than equal to 0. Assume x prime is a solution of 1, that is f of x prime greater than equal to 0 for all y. So this is, that means solving 2, you are solving the equilibrium problem. So now this is a equilibrium problem, but your this function, if you will define, take the difference as defined as f of xy, then getting f of xy positive is same as solving minimizing phi x belongs to k. That means how this equilibrium problem can be solved using optimization problem. Optimization problem also can be solved using your this equilibrium problem. Okay, so this thing, then calculus of variation also. So what is this Euler-Lagrange equation, Euler-Lagrange equations, because those are infinite dimensional problems, etc. Yeah, this is the optimization problem. You just, here we have a functional. Okay, so this is the time, this is the continuous case, because it is here the dimension is infinite. You are looking for a curve rather than a point. Okay, so you have to minimize j sub constants. So those constants are attached with some differential equations, etc. Okay, so with continuous first partial derivative, the Euler-Lagrange equation also can write fx ft f prime t dt fy t f prime t g, where fx fy t are the partial derivatives of f with respect to the second and third argument respectively. So it is similar to your gradient type, but we are calling that Euler-Lagrange equation, which satisfies in case of infinite dimensional problems. In control theory also we can use this. Okay. Then optimal control also is there. Those are also infinite dimensional problems, etc. Okay. So this part I am skipping. Okay. So this way, so we have to control that control problem. We have to control it, for which the system equation will stable. Okay, so that is what somehow you have to minimize a functional. So in the case of control problem, you have to minimize a functional. By functional, we mean it is a function from a vector space to its field. So it is basically that we just write in terms of is the state variable x, u is the control variable, to is the time. So in that case, we just denote this. So this is the standard like the linear differential equation we are using. So one common cost functional used together in this description in minimizing this j to infinity. So this is the quadratic part, and you have to minimize this quadratic terms, etc., where the matrices q are positive and definite. Uh, Respectively, note that the cost functional is thought in terms of penalizing the control energy measured as a quadratic form, and the time takes the system to reach zero state. So we have linear quadratic regulator also. These are the technical things used those electrical uh, uh, engineering. Then later on also we can talk about fractional calculus also to study this, but that part I am not touching because we just spend more time. So this part also is there, where fractional calculus, like even fractional order differentiation integration, also I can use to solve some of the control problems. Recently, those problems, those fields are very active. Okay, so this is like one problem I have solved it. So that value is first timing is just fractional optimal control problem also is there. Okay, yeah. So basically, yeah, this notion, because initially convexity, then invexity kind of thing, but recently those area is saturated. Now people don't like the notion of invexity. So you may divert the direction of invexity, etc. Because it has application when all those objective functions f0 and f are invex with respect to same vector. But if with different theta, you cannot get some good fruitful results. That is the reason as lot of restriction we are putting. So the notion of convexity is not so popular now. Many papers people have written in this field. This is a generalization of convexity with respect to this way. Because we have this when this is gradient x minus y, the notion of convexity. Now this is the definition of convex function. Difference of convex function. If we take x minus y as a function of xy, then we get popular now notion of convexity. That's what we have written. So this is Hansen discovered, but named by Graven in the year 1986. So many work has been done. Sufficient conditions also has been proved in case of inverse. That I am not discussing. So these are some of the references you can. Yeah. So this is my skill because this is related to fractional rational problem, programming. So this is a numerical optimization book A.B. Waldman, by Alan Brooks, and P.J. Whitey, Principles of Optimal Design Modeling. This is a book, Fractional Differential Equation, Introduction to Fractional Derivative, Fractional Differential Equation. Like 1999, this book. And you, this year, yeah. Okay. These are some of the references you can also see. Okay. So this is all about this fractional part. If you can interested, you can go through. Because we don't have time now to speak more, etc. Okay. So now I stop here. These are some of the references you can see. Okay. So this is all about this fractional part. If you can interested, you can go through. Yeah. Time now. Yes. Okay. So now I stop here.
papers, sir. Any question for participants? Thank you, sir.
Yeah, thank you very much. Yeah.
I request our organizing secretary, Professor Dipalendra Prasad, to give the vocal thanks.
Very good afternoon. One good to you from tonight. So, with this new enunciator, to give the board of hands to the dignitaries, speaker, and other teachers, and researchers, and students. First of all, I would like to thank Principal Dr. Satyadeep Viswal sir, who honored this function with his valuable thoughts and his enthusiastic support. I would like our esteemed speaker, Professor Dr. Chandranath sir, from IIT Kharagpur, for delivering his wonderful presentation on optimizing programming and its application. Thank you, sir, for your valuable talk. I would like to thank our beloved HOD, Professor K.K. Pusti sir, for organizing this national webinar. Also, I would like to thank the members of our organizing committee, Mr. Subrat, Mr. Mishra, who helped us prepare online propaganda. Thank you, Mr. Sir, for your kind cooperation. I thank all the staff members, our college, students. Last but not least, our beloved audience for their participation to make this webinar a grand success. Once again, thank you all for your kind cooperation and patience. Thank you all. I thank all the staff members, our college, students. Last but not least, our beloved audience for their participation to make this webinar a grand
Thank you, sir.
success.
Meeting is over.
For your kind cooperation and patience.
Okay, thank you.
পট্টাচার্য অলরেডি দিদি তোর
Thank you, sir. Meeting is over.